Okay, so in the last lecture we had seen the two approaches for designing the observer. So the first observer we had seen is given by x hat dot is equal to ax hat. Then we added one term which signifies y minus y hat, right? And we also parameterize this in the form of the into this form x hat plus bu plus ly. Okay. So this was one observer. Another observer we designed using the Lyapunov equation method. So that observer is given by z dot and here we had the output of this observer x hat is equal to t inverse z, where t was basically obtained after solving the Lyapunov equation, ta minus ft equal lc. Okay, so these two observers we had seen yesterday or in the last lecture. For the given plant, let's write the equation of the plant also. Let's call it the plant, and this one is the observer 1 and this one was the observer 2. Okay, so there are a couple of points which we want to highlight before we go on to the next topic within this module. So here you would notice that, say for example, if the plant is n-dimensional system, meaning to say that x is a n-dimensional variable, then both the observer 1 and observer 2 both were having the x hat of the similar dimension. So x hat was having the n dimension, similarly in observer 1 and similarly in observer 2, right? So we call such observer as the full order observer or the full order state estimator. Now in these two observer design, you would also notice that if I put t is equal to the identity matrix in this observer, then I would obtain x hat is equal to z, and then I can replace the state equation of this observer as x hat dot is equal to fx hat plus bu plus ly. Okay, now if I substitute t is equal to I into this Lyapunov equation, I would get a minus f equal lc, or I can replace f by a minus lc. So if I substitute this here, so I would get a minus lc x hat, excuse me, plus bu plus ly. Okay, so basically both observers are now the same. It's just the synthesized procedure of the f matrix and the other associated matrix in the two observer design. Okay. So today we will introduce the reduced dimensional state estimator, where if x is an n dimension, x is of n dimension, then we need to design the observer whose state is lesser than the n dimension. Okay, so if it is possible, then we call those observer as the reduced dimension observer or the state estimator. So the first question arises here, that whether such kind of reduced design is possible or not. So if we go back to the definition of the observer canonical form, so that if the system is observable, then the system can be transformed into the observable canonical form as this one. So here we have considered the one specific case where n is equal to 4. So we had discussed at several places the significance of this word canonical, because if say for example for a system, it could have many state space representation. Now it might be possible that in some state space representation, x is not directly appearing into the output measured variable. Okay, but if we carry out the canonical transformation, then depending on the dimension of the C matrix or the output matrix, some of the states would directly be available in the output measurement. Okay, so here this is one specific example where n is equal to 4. So once we convert this into the canonical form, we see that y actually becomes equal to x1. So x1 is directly available in y. Okay, so but we still need to estimate x2, x3 and x4. Okay, so for only estimating those states we can design an observer. So this is one specific example. So therefore it is sufficient to construct an n-1 dimensional state estimator to estimate xi for the rest of the state variables. Okay, this estimator with output equation can then be used to estimate all n state variables. So this estimator has a lesser dimension than the dimension of the plant. So and we call it the reduced dimensional estimator. Okay. So here we will see one design procedure which is based on the Lyapunov equation. So if we recall the steps what we had seen in the full order observer, there we select an arbitrary stable matrix F of dimension n. But here we select an arbitrary matrix of dimension n-1 which is lesser than n. And in addition that the eigenvalues of this F matrix are not common with those of the A matrix. The next step is to select the vector L of appropriate dimension such that this pair F comma L is controllable. Next we solve the Lyapunov equation to compute this matrix T of dimension n-1 cross n, and then finally by using the state equation what we had seen earlier, we can estimate this x hat. So here you would notice that the state equation of the observer where the state variable is defined here by z remains the same. Okay, it just the dimension of the associated matrices would change. And here x hat we see it is given by the inverse of this matrix formed by concatenating two matrices C and T and vector y and z. So here we say that this x hat is an estimate of x. Okay. So in the previous full order design for the single input single output system, we ensured the invertibility of the T matrix. But here since there is another element which is being inverted, so we need to see whether this matrix is always invertible or not. Okay, first of all we will go to the justification of this procedure, that whether this state estimator actually give us the estimate, and then we will comment on the invertibility of this matrix. Okay. So we write x hat which was the output equation as yt zt is equal to, so suppose that it is possible to take the inverse of this matrix, so I can write this one, which I can write as p times x hat, where p is that matrix of which I need to show the invertibility. Okay, on which we will come on to later. So if we see the first element and the second element, I can write individually or separately as y is equal to cx hat. So this y become equal to cx hat and this z become equal to tx hat. Okay, now since here we can see clearly that yt is an estimate of cx. So now we need to show that zt is actually an estimate of tx. Okay, then in that case we could say x become equal to x hat. So again writing or proceeding in a similar way, first we define the error vector as z minus t times xt, and then taking the derivative of this error equation and substituting this z dot and x dot from the plant, we get this. So in a similar way some of the terms will cancel out and some of the term after combining would finally give us that this relationship, that E dot become equal to FET. Okay, so we have already selected F as a stable matrix, so it ensures that E of t would tends to 0 as t tends to infinity, thus Z is an estimate of Tx. Okay, so we see that this reduced dimensional state estimator helps us to estimate the complete state, though the dimension of the estimator is not the same as the dimension of the plant. But still we need to ensure the invertibility of the P. So this result uh, talks about the non-singularity of this P matrix. So if A and F have no common eigenvalues, which we have already ensured in the design step by selecting this F matrix in such a way that both these matrices do not share the same eigenvalues. Then the square matrix defined by this, by combining this C output matrix and the T matrix, where T is the unix, or where the T is basically obtained by solving this Lyapunov equation. Okay, so this P matrix is non-singular if and only if this pair is observable, A comma C, and F comma L, so this should be small l, F comma L is controllable. Okay, so we need the observability of the pair A comma C, which we have already ensured, or which is the basically the primary condition for the existence of the observer. Second, this pair should also be controllable. If both these conditions are satisfied, then it is always, then whatever the P matrix we have obtained would always be non-singular, because this is if and only if condition. Okay, so we shall not go into the proof of this result, which we had seen at numerous occasions. So now we'll move to the next topic, which speak about the feedback from the estimated sales. So this was the main issue with which we started our 7th week, that the state X, by using which we want to design the state feedback, is not possible to measure directly. So we have designed this observer. So let's see that if we combined both the, say, the observer and the controller, then how the design or the dynamics of the overall closed loop system would behave, right? So let's analyze this first. Given this plant, we know that the pair AB is controllable. Then we can design the state feedback, which is we had seen earlier, that U is equal to R minus Kx, where R is the reference signal and K is the state feedback gain vector. Can place the eigenvalues of this A minus Bk in any desired positions. Okay, we had also seen that under stabilizability, or if this pair is stabilizable, then still we can design the controllable. Okay, so if the state variables are not available for feedback, we can design a state estimator to estimate this X hat. And then finally, so for this design of the state estimator, we need to ensure that the pair A comma C is observable. So we can design either a full dimensional estimator or the reduced dimensional estimator with arbitrary eigenvalues. Okay. Now if this pair is detectable, we cannot place the eigenvalue arbitrarily, but still we can ensure the asymptotic stability of the aerodynamics. Okay, so let's see. So consider the n-dimensional state estimator. So here we are considering the full dimensional state estimator, though the analysis would remain the same for the reduced dimensional observer. So this equation we had used earlier, x hat dot A minus LC x hat plus BU plus LY, where A minus LC is a stable matrix and LY is a output injected term. The estimated state can approach the actual state with any rate by selecting the vector L. Okay, so we have already assumed that the pair A comma C is observable. Now if we design the controller, if X is not available, it is natural to apply the feedback gain to the estimated state S. So earlier we had seen that the controller was U is equal to R minus Kx. Now instead of using X in the controller, we are using X hat, which is coming from the estimator. So if we see the block diagram representation, this is the plant having input output U and Y. So taking these two signals u and y, we estimate this x hat, and then this x hat we have further used to design the state feedback controller, which is given by u is equal to r minus k x hat. So we call this configuration as the controller estimator configuration, where obviously this part or the state feedback, we have the controller and it is taking the input from the estimator. So after seeing this connection, there are some questions which arises naturally. So the first one is that the eigenvalues of this A minus Bk, which we have obtained this matrix after applying only the state feedback, are obtained from this one. So do we still have the same set of eigenvalues in using u is equal to r minus k x hat? Yeah. So this question basically implies, let's say for example, if we do not have this estimator, okay, and we have direct measurement of x, and instead of using this x hat, we are taking this one. Okay, so we had seen already that the closed loop state matrix would be A minus Bk. Now if we are using this estimator, whether the eigenvalues of the closed loop system would still remain the same or it would change. Right? So the second question, will the eigenvalues of the estimator be affected by the connection? So it is both ways. So whether the eigenvalues of the closed loop control system would be affected by the estimator or vice versa. Right? So now what is the effect of the estimator on the transfer function from R to Y? So earlier we have derived the transfer function of the closed loop system. Now there is an estimator block inside it. So this question naturally arises whether this estimator would have any impact on the transfer function, in the sense either the transfer function would change or would it going to remain the similar. Okay. So we'll try to answer a couple of most of the questions in this connection. So to answer these questions, we'll develop first of all the state equation of the overall system to further analyze that what is happening inside the closed loop. I will write here the equation of the plant also, which is x dot is equal to ax plus bu. Okay, so this estimate okay, and we write u is equal to r minus kx hat, right? So now this is the plant, the actual plant, and this is the controller, that instead of having this x, we are supplying it x hat. Now if I combine these two systems or these two equations, I would get this one, x dot is equal to ax, and putting u as r minus kx hat here, I would get br minus bk x hat. Okay. Now seeing the second equation, which is basically the estimator, that this is the estimator where we have x hat dot is equal to a minus lc x hat plus bu. Now here we have also replaced u by r minus kx hat, and plus, and the last term is ly, or we can write y as cx. Okay, so this is, you can see the plant plus controller, and this one is your estimator. Okay, so now we will make a new system by combining these two state equations into one, as we will write this, let's say, we will come on to this later. So we can see that this x dot and x hat dot would become a new state vector. Let's it's better to define them. Let's call them x tilde. Okay, so it would be x tilde is equivalent to this one, and this we have defined it as x tilde. Okay, so it becomes x dot is equal to ax, this term, minus bk x hat minus bk x hat plus br. Okay, this is the first equation. The second equation is x hat dot is equal to, we need to find out all the terms with respect to x, so LCX, then we have a minus LC minus bk times x hat. Okay, so this becomes this element of this matrix, and the last element is b times r. Similarly, the output equation will become cx hat and 0 times x hat. Okay, this is pretty much straightforward. So if you see the dimension of this overall new state space system, it would be 2n. The n state variables are coming from the plant, and similarly the n state variables are of the estimator. So the overall dimension of the state space equation in 2n. So this system describes this overall feedback system where we have both the controller and the estimator. Okay. So now we introduce the following equivalence transformation. Now we define this another state, let's say x bar. Okay, and this one we had x tilde. So I make a new state vector called x bar, which is basically x and e. X is the state of the plant and e is the error vector, which is described by the difference between the actual state and the estimated state. Okay, so this is basically an equivalence transformation which we had seen in the first week. So if we see at the outset, we would get x bar is equal to p times x tilde, where x tilde is the state variable of one representation. I want to transform into another representation whose state is x bar, and I am using this p. Now if you see the structure of the p, this p is non-singular. Okay, and so let's do the equivalent transformation. So we can also see that p inverse also become equal to p. So now if we define the state space system into this new state variable, and after simplification I would get this state matrix, B matrix and the C matrix. Okay, so you can do this by yourself also by using the formulas which we have introduced in the first week, where we spoke about the transformations from one representation to another representation. Okay, so this representation is basically equivalent to the representation we had seen in the last slide, which was in terms of x tilde. Okay, so now after using this transformation, many things have been highlighted, so we can see one by one. So this is the next result, the closed loop of the process, basically, which is this estimator plus controller system with the output feedback controller, results in a system whose eigenvalues are the union of the eigenvalues of the state feedback closed loop matrix A minus Bk with the eigenvalues of the state matrix A minus Lc. Okay, so pay attention to this state matrix. So now this is upper triangular matrix, and if we compute the eigenvalues of this matrix, you would see that the overall or the eigenvalues of this state matrix would be the union of this eigenvalues of this matrix and the eigenvalues of this matrix. So the eigenvalues, so that's why we say that this is a separation property, that, and it also speaks about that both the controller and the estimator can be designed separately. No one has any effect on the other. Okay, let's see some couple of more observations. So this was the estimate control or the closed loop dynamics we have obtained. So inserting the state estimator does not affect the eigenvalues of the original state feedback, nor are the eigenvalues of the state estimator affected by this connection. So this we had already seen. Second, so as a consequence of this first point, the design of the state feedback and the design of the estimator can be carried out now independently. Third, the which is most interesting, that if you see the state equation of this overall closed loop dynamics, it is not controllable, right? So pay attention to this state equation. So once we have used the transformation, we have actually end up with the decomposed form, where this, if we write the dynamics of the second state, which is E, so this becomes E dot is equal to A minus LCE, because we have this 0 here. So this E is not all controllable, but at the same time we have ensured that A minus LC is stable matrix. So this state equation, although not completely controllable, but still it is stabilizable. Okay, so this is just one observation, although we won't be using it in closing any feedback loop or designing an observer. Now talking about the transfer function. So if we compute the transfer function of this one, it basically equals the transfer function of the reduced equation of this one, which we had already seen by G hat F, which is the transfer function of the feedback system. It is given by this one. And as a consequence of this, the estimator is completely cancelled in the transfer function from R to Y. Right? Because the last equation, which is E dot is equal to, let's say, A minus LC times C, this is a homogeneous system. And this won't appear anywhere in the input-output signals. That's why we are getting the same transfer function what we were obtained when we had not used any estimator. Okay. So this was all on the feedback from the estimated states. So now we can see or we can quickly go through all the results under the multivariable environment that consider the n-dimensional P input Q output state equation, where we have now capitalized the matrices B and C because they are no longer the vectors. So the problem remains the same, that the input and output are available to us, and also we have the knowledge of the matrices. So we need to compute X given the information of U, Y and ABC. Okay. So we can extend the previous study to the multivariable case as this one. So this observer, we also call it the Leuenberger observer, which is X hat dot is equal to A minus LC X hat plus BU plus LY. So this is basically the full dimension observer. Okay. So by seeing in a similar way, that we can first define the error signal as a difference of the actual state and the estimated state, and then taking the derivative and substituting these two state equation into the derivative of this error, we would finally end up having these error dynamics. Okay, where we know that if the pair A comma C is observable, then all the eigenvalues of this matrix can be assigned arbitrarily by choosing an L. Okay, if this AC is detectable, then although we cannot put the eigenvalues of this matrix arbitrarily, but still we can ensure the stability of this matrix so that the error dynamics will be approaches to 0. Okay, so the full order design would remain the same. There is a slight change in the reduced state estimator, which we can see. So we won't be discussing the design procedure of the full order state estimator, which you can do by using either of the method, that is eigenvalue assignment or the Lyapunov equation method. So here we would see the reduced state estimator. So we have this n-dimensional Q output observer pair A comma C, where we have assumed that the matrix C has rank Q. Okay. Now the first step, we select an arbitrary matrix, stable matrix F of this appropriate dimension, which shares no eigenvalues with that of the A matrix. Again, the next step, we select L matrix such that this F comma L pair is controllable. Then we compute this matrix T by solving this Lyapunov equation given by this. Okay, So if you recall that in the single input single output case, we had formed this P matrix as the combined matrix of C and T. So if the square matrix of order n, this one, is singular, then we go back to step 2, this one, and repeat the process. Okay. So we need, this means to say that we need to find another L matrix such that if we put that L matrix into this Lyapunov equation, we would obtain another T matrix. Okay, so for some L matrix, this P matrix would definitely be non-singular. Now if P becomes non-singular by carefully selecting this L matrix or F matrix, then this n minus q dimensional state equation, which is given by this one, where the first equation remains the same, and x hat generates an estimate of the actual state. Okay, where this is our P matrix. So again, the problem here we see in the algorithm that P could easily be a singular matrix. Okay, because in the single input single output case, when we had ensured the observability of this pair and the controllability of this pair, so it is always true that the P matrix would be non-singular. But although we have ensured these two conditions in the multivariable environment, still we cannot ensure the non-singularity of the P matrix. Okay, so we will see what we can say at least of this P matrix. So now if we go through the similar procedure to ensuring whether the designed estimator is basically give us the estimate. So this is the standard procedure what we can what you can follow. Okay, now this is the main result. So basically this is only the necessary condition, that if the matrix A and F have no common eigenvalues, then the square matrix P, which is formed by combining C matrix and the T matrix, where T is basically obtained by solving this Lyapunov equation, is non-singular only if this pair is observable. Okay, this you can also understood in a way that let's take this second statement, okay, and take this as a first statement that the P is singular. Okay, now it says that first that P is non-singular. If P is non-singular, then it will always, the second condition would always be true. Okay, but if the second statement is true, then it does not imply the first statement would also be true. Okay, this we had already seen in the algorithm also, basically, that although we have ensured the observability of the pair AC and the controllability of the pair FL, still we can end up with having a P matrix which is a singular matrix. Okay, so here in the multivariable case for the reduced state estimator, we have a weaker condition which is only necessary, not the sufficient. Okay.